are on our final section, and we're going to look at the graphs of inverse functions, which is section 5.5. And I'm going to start with some notes on what is an inverse function. There are three that you need to be concerned about, and this one here is also called arcsine. So if you ever see arcsine S, it means that. And we pronounce that, or we say that out loud as the inverse sine of x. And it's basically the opposite of the sine function. From 141, do you remember that there was a function and then a lot of functions had another guy called the inverse function? So x squared was your function and wasn't the square root of x your inverse, you know, those kind of things. X cubed was your function, the inverse was the cube root of x. It's basically the function that would undo the first one. So we're going to be looking at an inverse sine, and it looks like this. And the way I look at it, if someone went and said to me, the inverse sine of a half, right? So that would be about here. And you get this number here. The inverse sine of a half is what angle, this is in English, gives you a sine that's equal to a half. So the inverse sine function tells you angles that give you particular sines. Now you look at the shape of this fella, it's quite interesting. It only goes from -1 to 1. And the reason for that is you can't get an angle whose sine is 2. Would you agree they don't exist, right? The biggest value a sine function can ever be, right, is 1. And the smallest it can ever be is -1. So the domain is -1 to 1. And the range of this function is -pi/2 is the smallest angle you'll get of an inverse sine, and +pi/2 is the largest one. So if you're looking, and that's a kind of strange way to do it, but that's the way that they've decided to do it. The answers that you get from an inverse sine function, you only get angles from the first and the fourth quadrants. So an inverse sine function only gives you angles that are in the first or fourth quadrant, and that'll become important later. Now the inverse cosine function looks like this, and its domain is from -1 to 1 for the same reason that this one is. You can, the biggest value of a cosine can be as -1, and the smallest is -1. And then if you do the range, well, the angle that you get when you use an inverse cosine function is the angles are somewhere between 0 and pi. And that means that when you use an inverse cosine function, the angles that you get are from the first and the second quadrant. And for the final one, the inverse tan. That guy oh dear, that was a horrible drawing, sorry about that. This is what the inverse tan looks like. Also called the arctan. And its domain is all real numbers. A tangent can take any number, right, from -1 trillion to +1 trillion, right? Any value at all. And its range is the same as this fella. The answers you get are always going to be angles between -pi/2 and +pi/2. So that's pretty much all you need to know about what the graphs are. That the inverse sine looks like this, that the inverse cosine has a different shape and the inverse tan looks like this. And I'm now going to show you that you can use Desmos to draw sketches. Right, so if you ever really wanted to look at one, let's close these guys off, move this up a little bit. Can you see from -1 to 1? And you can see negative pi upon 2 to plus pi upon 2. To see that is the inverse sine. Now, if I click on this one, maybe make that one go away, maybe bring it up a bit. There, can you see the inverse cosine one that I drew? And can you see it goes from -1 to 1? And this time the angles that you get are from 0 to pi. And I'm going to put down here the inverse tan, which is called arctan. And that guy really can go, well, anywhere you like. So I'm just picking 40 -4 because I can't do infinities. There. Go away. Right, can you see the inverse? Let me shrink it back a little bit there. Can you see the inverse tan in its weird shape? Now, I discovered something new that I kind of like about Desmos. Have you noticed that these guys have pies in them and quarter pies? Isn't that quite helpful if you want to draw a picture and you want pies and you don't want 3, 4, 5? And I found out today how to do that. So let me share with you how you do that. Click in the little graph settings, right? Type in whatever you want and then just make the step, say, a quarter pi. So on this side here, let's say I wanted -2 pi. And here I would like 2 pi. You see? Right. Now, if you want the x values, you know, because you want to do a sine of x or cosine of x, well, let's put 1 in. Let's get these guys out the way. Let's suppose I wanted to do y equals 2 times the sine of 3x, right? And I want to, that's what it looks like, and that's fine. But I'd like to see the x values with radians in them. So I'm going to go here, and I'm going to go -2 pi, and I'm going to go here. I'm going to make it +2 pi, and then in the step you could put, I don't know, say pi upon 4, because I want it, and I should be able to cut it. Do you see that it now puts pi's on the x-axis? Zoom in. Can you see it? I think that's a cool little feature. Desmos has got 1,000 things I don't know how to do, but you know, now and again I never knew how to do that, and now I do. So far so good. So we have 3 new functions. They are called the inverse sine functions, inverse cosine functions, and inverse tangent. So we are now going to do.
I have a question really quick.
Go for it.
On your arc sine picture, the Desmos, it's supposed to, like, it shows that it goes like the opposite, like the curve is wrong compared to Desmos.
Did it? Let me check that.
I saw. I don't know if I missed it.
Oh no, it's not. I'll go back. You might have been looking at the inverse cosine, and maybe that's what was distracting you. Right, I'll zoom back and I'll show you the inverse sine function in all its glory. Do you see the way it's curving? Oh, I see what you're getting at. I can't draw curves.
Okay.
I did it like an S, but I did a bad kind of S. I should have done an S going like this and not an S going like that. So I agree with you. My inverse sine wasn't quite as nice as it could be. You're right. It still has the basic features, so it's not wildly wrong. Right. So, done. How do you find values for inverse? Using this fella. Remember our unit circle? if you're being asked to find the value of an inverse sine, cosine, or tangent, for instance, the inverse sine of root 2 over 2, right? Imagine you were asked to get the exact value for that. Now, in English, what that would become is the angle whose, well, since it's a sine, isn't it, the y-coordinate, is equal to root 2 upon 2. Now, if you go and you look at the unit circle and you find the angles that have a y-coordinate of root 2 upon 2, you're going to get two answers, but only one of them is correct. Would you agree that pi upon 4 has a y value of root 2 upon 2? Great. So one of my angles is pi upon 4. There is another angle over here that also has a y-coordinate of root, and it's that one. But only one of these is the answer that you're getting, which brings me to what I was talking about when I said you can only get your answers from the first and fourth quadrants, okay? First and fourth quadrants. Now, did you notice that the two answers were here and here? So the answer that you're going to use is that one. So the inverse sine of root 2 upon 2 is unique. In other words, there is only one angle for any given usable value in here, right? And so when you're doing a sine function, in fact, I should probably put that somewhere. I'm not quite sure where. I'll write it in the bottom here. If you're doing an inverse sine, then your answer, which is an angle, has to be in the first or the fourth quadrant, right? That's the only places you can pick. If it's an inverse cosine, can anybody remember what two quadrants you get your answer from in an inverse cosine? I only fleetingly mentioned it, but did anybody remember it?
1 and 2?
Correct. And then if you want an inverse tangent, it's the same as that guy. So it's back to angle 1 and 2. Okay, so keep that in mind. So if I gave you the inverse cosine of root 3 upon 2, in English, you wouldn't write this, but this is from notes. You would be looking for the angle whose x coordinate is equal to root 3 upon 2. So let's get this guy here. If you look for root 3 upon 2 as an x coordinate, would you agree it's pi upon 6? Right, x coordinate, root 3 upon 2 is the angle pi upon 6. Now there is another possibility, but it's down here, and we only want the answer, okay, in the first or the second quadrant, and that guy is the first quadrant, and that's your answer then. So there's going to be a lot of questions where you're basically going to do what I just did. You are going to be finding inverse sines and inverse cosines using your unit circle when at all possible. So here are some examples. The inverse sine of -1. Okay, so I'm looking for an angle whose y-coordinate is -1, and bearing in mind that your answers have to be in the first or the fourth quadrants. Okay, what is the only angle in the first or fourth quadrant which has a y-coordinate of -1?
Would it be 270?
Yep, 270 degrees, and I think you're right, but we're going to use radians because Weber sign just wants everything in radians. Are we good with that?
Does that count as the fourth quadrant, even though it's like
It's kind of bound, but it's the only one in town, isn't it? So I guess it doesn't matter.
Okay.
Right? Technically, it's in both at the same time, right? But it's only one place. So let's give you one like this then. How about negative? There are only so many answers you can actually be given, right, in a unit circle. How about that one? Now, since it's inverse cosine, the answer has to be in the first or second quadrant. So I'm looking for an angle whose x coordinate is -1/2. So which angle in the first or second quadrant has an x coordinate of -1/2?
2π/3.
Check it out. Would you agree? So your answer, 2/3 pi. And now I'm going to hit you with a trick question. I'm warning you, it's a trick question. What is the answer to the inverse cosine of 4?
It is undefined because there's no, can't go past 1.
So does not exist is what you write there, right? Great. What about the inverse sine of -2? Anybody? What about that? Any takers?
It doesn't exist.
It was very quiet. Someone definitely tried to say, I think it was Anthony. What did you say, Anthony?
It doesn't exist.
Yes, does not exist. If you have a number in the inverse sine or inverse cosine that is bigger than 1 or less than -1, as we have here, doesn't that mean the answer just does not exist, right? There is no angle, right? There is no angle in a unit circle that has an x coordinate of 4. There is no angle in the unit circle that has a y coordinate of -2. Agreed? So when those appear, it's DNA is your answer. Does not exist.
And is that because of the domain or just because of how the unit circle?
Yeah, it's to do with the domain. The domain is only from -1 to 1. So you're not allowed to use numbers outside of -1 to 1. So that's one of the reasons. And the second reason is just a practical reason, right? Would you agree there are no angles with an x coordinate of 4, right? There just aren't any, and there aren't any with a -2. So the domain is just reflecting that, right? When the domain says -1 to 1, it's reflecting a fact we already know, that you can't get numbers bigger than those two guys, right? That's the extreme values that you could get. You want to see some more of these, or you feel comfortable that we could do inverse sines and inverse cosines as long as the angle is in a unit circle?
How do we do an inverse tan?
It must be your mic or my hearing. So I'm going with your mic. So what is it you're asking, Anthony? I can't hear.
How would you do an inverse tan?
You are asking a really good question, and I am not going to tell you yet. We're going to concentrate just a little bit longer on this inverse sines and cosines, because the inverse tangent is quite hard, right? And that's like a special situation. But I will tell you, but not quite yet. But we're coming to it. Let's look at finding inverse sines and inverse cosines of numbers that are definitely not in the unit circle, right? You know, when you're doing unit circles, aren't the answers, you know, the numbers that go here, a half, √3 upon 2, 0, right? You kind of know those. Well, what you do is you use a calculator, and when you get these questions, they will, actually, I just noticed something here. WebAssign wants you to use the word undefined, which is what Katie Wynn said earlier. Right. So back to this guy. The inverse cosine button and the inverse tan and the inverse sine, they're all here. They're on the same place as the sine, cosine, tan. They're just inside the second feature button. Now what I'm going to do is make sure that I'm in radians, because that's pretty much the go-to unit. And you want to find this guy, you just go inverse sine, 0.23. And let's suppose they want the answer to 3 decimal places. So 0.232. And if you want an inverse cosine of negative 1.75, try that again, inverse cosine of negative 0.75, you get that. Now, the one I had in a minute ago, I should have realized that I don't need a calculator to do that one, because isn't that does not exist, or as WebAssign wants to call it, it's undefined. But let's try and calculate it anyway. If you go the inverse cosine of negative 1.75, I'm about to hit enter. Watch what TI-84 does. Error in the domain, right? You try to pick a number that doesn't exist. So the calculator knows when things are impossible as well, doesn't it? Would you agree that's pretty straightforward then? If you're looking for ones that aren't in the unit circle, it's just press some buttons on your calculator, right? Clear. And round off to 2, 3, whatever decimal places. Now it's time for me, Anthony, to talk about the kind of elephant in the room, which is how do you do inverse tangents, right? Well, I'm going to work backwards. We're going to do them using the calculator first. Now, one of the things about the inverse tangent is its domain is all real numbers. In other words, you can get an angle whose tangent is 800. It can happen. So there are never going to be, you know, undefined or does not exist here. So inverse tangent of 1.3 is simply 0.915 radians, right? Because you get an angle when you do these. The inverse tan of 3.7 ends up being 1.307 when you round it off radians. And this fella, the inverse tangent of negative 0.71 is going to be negative 0.617. So it's pretty easy to do inverse tan of things that are not, right? Things that are not in the unit circle. But now we're going to do guys who are in the unit circle. And this is where it gets a bit messy. So for instance, I would like to know the inverse tan of 1. And I know that the answer I'm going to get has to be in the first or fourth quadrant, right? Now, we're looking for an angle, right? The inverse tan of 1 is an angle. And it has the property that the y coordinate divided by the x coordinate has to equal 1. So basically, don't we have to scan through all of these coordinates? Basically, I only need to look here, first and fourth quadrant, right? And we have to find an angle whose y coordinate divided by its x coordinate is 1. So it's not so easy, but if you look carefully, you should be able to tell me what angle actually is that true for.
Is it pi over 4?
It is. If you take that and divide it by that, do you agree you get 1? Someone in this class came up with a really cool way of kind of dealing with the fact that you are going to divide an awkward fraction with an awkward fraction, and it kind of went like, don't care what the bottoms are because they're going to cancel out, right? You don't care about the 2's. So if I was going to divide those two, wouldn't the answer be √3, right? Y over x, √3 over 1. If I was dividing those, wouldn't you get √2 over 2, which is 1? If I was dividing those, wouldn't you get 1 over √3? Can you see that? Okay, so I want to find an angle whose inverse tan is √3. So in English, we're trying to find an angle whose y coordinate divided by its x coordinate is √3. And again, we only need to look in these two quadrants. And since the answer is positive, I only really need to look here, because if you used any of these, wouldn't the answer be a negative number, right? So one of these angles here that you can see has the property that if you take the y coordinate and divide it by the x coordinate, it's √3, right? So let's take them at turn. If I start with pi upon 6, and I cover that up there, let me see if I can do something. Yeah, this might work. There we go. If you take pi upon 6, right, that angle there, isn't it 1 over √3? That doesn't work. If you did this one, here we go, wouldn't it, right there, touch, wouldn't it be √2 over √2, which is 1, so that doesn't work. If you go to this one, isn't that √3 over 1? Yep, that's the right one. Do you see that one there is the right one? And that happens to be pi upon 3. Which angle do you get when you find the inverse tan of 1 over √3?
Pi over 6.
Pi over 6. In a lot of ways, isn't that going to be easy? Because there's only a few answers that it could be. And here are the other two on the positive world. What angle will give you an inverse tan of 0? The y divided by the x is 0. What angle is that true for?
0.
I hear 0. Because it's 0, the x, 1, the y. Right? Do you see that works? Now, this one here says infinity. It's fine. Infinity is allowed now. Can you see it's that one? What angle has a tangent of infinity? Well, wouldn't that be 1 divided by 0? Do you know 1 divided by 0 is essentially infinitely large? And so that ends up being, and I think someone was going to mention that as a different answer, that's pi upon 2. So actually, haven't we covered every possible angle that you could get in the first quadrant? Now I'm now going to do the same thing, but we're going to do all the ones that come down here, and we'll show you what they look like. So I want to know what angle has an inverse tangent of -1. What angle has an inverse tangent of -√3? What angle has an inverse tangent of that guy? What angle has an inverse tangent of 0? And finally, what angle has an inverse tangent of -infinity? And actually, once we do these 5, haven't we done every single question you could ever be asked? Because that's the only ones that exist on a unit circle. Now, have you noticed that all these answers are negative? And that tells me that I'm going to be getting them from, right, the 4th quadrant. And try to find ways of covering things up. There, let's cover that up so it doesn't distract us. And we're only interested in guys in this quadrant. So this one here would be what angle, if you take the y coordinate and you divide it by the x coordinate, you would get -1. Okay, what angle is that true for?
7 pi over 4.
I hear you all doing it. And here's something you don't like. You are correct, but only half correct. It is 7/4 pi, none wrong with that. But the way the inverse tangent function works is they don't give you answers from 0 to 2 pi. If you're in the 1st quadrant, the answer you get is the right angle. But when you're in the 4th quadrant, you don't tell me it's 7/4. You tell me it's -1/4. In other words, negative inverse tangents lead to negative angles. Would you agree -1/4 is the same thing as 7/4? But -1/4 is the right one. If you went to that inverse tan graph and you went and tried to read off the answer, you would find out the answer was negative something, right? In this case, -1/4. So you remember when you're doing inverse tangents of negatives, the answer, all of them are going to be in the 4th quadrant, and the answers are always going to be negative because of that. Okay, so our next guy is this fella. So I'm looking for a y coordinate divided by an x coordinate, and it has to equal this fella. Which one of these angles, if you take the y and divide it by the x, right,
5 pi on 3.
And how are we going to convert that into the negative equivalent? So 5/3 is half right. Let's go 100% right. So what's 5/3 going to be?
-pi/3.
-1/3 pi, right? Or pi/3. Okay. This guy here is what, 11/6? Great. That one's 11/6. Of course, that ends up being -1/6, right? We don't give the answer as a positive. When your answer is in the 4th quadrant, the inverse tangent should always return this one. What one gets me a 0? Well, actually a 0 we've done, isn't a 0 in the boundary, so it's basically that one. And -infinity is 3/2 pi. But what does 3/2 pi get written as?
-pi/2.
-pi/2. Right. Are you comfortable with inverse sines, cosines, and tangents now? Right. And be careful when you do inverse tangents to take your answer and convert it into a negative equivalent. And also if you're doing inverse sine, I should say, for the same reason. So see if you get an angle and it's 7/4 pi, right? Well, you remember to turn angles like 7/4 pi into -1/4 pi, right? So any angle that appears in the 4th quadrant, write down its negative version. And that's how the inverse trig functions are evaluated. Scanning through those guys, and they are good. And for our next piece of work, it's going to be number 3. Is it? Oh, we've done 3. So we're on to our last piece of the puzzle then. Evaluating expressions that contain both things. So here is our first thing. If I ask you to find the sine of the inverse sine, oops, of a half. So that I'll write that down again. The sine of the inverse sine of a half. We would do it something like this. First thing I would do is I'd find what angle has a y coordinate of a half, and it's in the first quadrant, and that's pi upon 6. And I would do the sine of pi upon 6. And what is the sine of pi upon 6? The answer is a half. Do you notice that those two things essentially cancel out, and that's why you end up back at a half? Does that make sense? It's a bit like somebody saying, what's the square root of 5 squared? Isn't the answer just 5, right? They kind of cancel out. Now, suppose I said to you, what's the cosine of the inverse cosine of root 3 upon 2? What do you think the answer to that's going to be without doing the intermediary stage?
Root 3 upon 2.
Root 3 upon 2. And then just when you think you've sussed it out, we put a curveball in. Oh, it's important that that's negative. Right. So let's see if negatives make a difference. Well, if you go looking for the fourth quadrant with a y coordinate equal to that, you end up with 7/4, or as we would write it, -1/4. And the sine of 7/4. And you get back to the guy you started with. Are we comfortable with that? So it doesn't seem to matter if it's a plus or a minus, right? We got this. So here is a trick question. And I'll tell you what the answer isn't. It's not 3.
Does it
Undefined.
not exist?
It doesn't exist, or as Webersine would say, it's undefined. So can you see you might get caught out if you get too caught up on, yeah, they cancel out, no biggie, right? Most of the time, don't they? They cancel out exactly the way they should, right? Now, let's switch places. I'm going to do an inverse sine of the sine of pi upon 3. What do you think the answer should be this time? What's your gut feeling? You might be right, you might be wrong, but what's your
Pi
gut
over
feeling?
3?
Yeah. Well, let's find out. It's a unit circle kind of question. I'm going to do the inverse sine. The sine of pi upon 3 is the y coordinate, which is what? Root 3 upon 2. The inverse sine of root 3 upon 2 is what angle in the first quadrant has that? And yeah. Hey, that matched up, didn't it? Everything's cool. Try this one. Right, negative pi upon 3 is basically this guy here. And so its y coordinate would be negative root 3 upon 2. And the angle that gives you that is pi upon 3. So, hey, that's a good match. And then just when you think everything is fine, Let's put the cat amongst the pigeons. Shouldn't that answer be 5/4 then, right? It looks like inverse sines and sines just cancel each other out, and whatever you started with is the answer, right? Whatever you started with is the answer. So it would be reasonable to assume that this answer is 5/4. Great, but it's not. The sine of 5/4, right? If I find 5/4, here it is. The sine of 5/4 is negative √2 upon 2. Now, the inverse sine of negative √2 upon 2 is an angle in the 4th quadrant. And the angle that it's going to be is this guy, which becomes negative 1/4 pi. Do you see? They don't match. So my advice to you is, if you're ever doing one of these combinations of sines and inverse sines, right? Cosines and inverse cosines. If you're a gambling person, won't the answer be the same as the guy you started with? But isn't there a possibility that it might not be? So isn't it safer just to do it the long way in case the one that you're doing is like this case here, right? I'm assuming that half the time you're going to get the guy you started with, right? But at least some of the time, isn't one of these things going to happen? Now, the only other combination is when you take cosines and inverse sines or inverse tans or whatever, and you do that term. So we want to find the cosine of the inverse sine of a half. So I'm going to do a positive version of this and a negative version, and that's all we'll have time for, right? The inverse sine of a half is what angle in the 1st quadrant has a y coordinate of a half, and that is pi upon 6. And the cosine of pi upon 6 is √3 upon 2. So there's your answer. Now, if I do the cosine of the inverse sine, but now I choose, I don't know, negative √3 upon 2. First thing you do is you find the angle in the 4th quadrant that looks like this guy, and that happens to be 5/3, right? This angle here, and 5/3 is what? Negative pi upon 3. Of course, the cosine of negative pi upon 3 is 5/3, so that's not a big deal. And the cosine of this guy is 1/2. You comfortable with how we got that? So you find this answer, and then you find the cosine of that answer, and everything is going to come from your unit circle. And typically, isn't it going to be one of these numbers along the outside, right? Plus or minus of. Now,
So
I just
first sine, like when you draw it out, doesn't it go in like the 1st and 3rd quadrant?
it goes in the 1st and 4th. It's 1st because it's positive, and 4th because it's negative.
Oh, that's weird. So like we in like the when you drew it on Desmos, like it goes like in the 1st and 3rd.
Oh, let me bring that guy up. If I got it, I've got it in front of me. Good.
Yeah, maybe I'm just really confused.
Now, the quadrant you're talking about, I understand what your question is, and let me try and explain why you're kind of reading it wrongly, right? You're saying, oh, 1st quadrant, 4th quadrant, right? That's how you're saying this, but that's not what you should be reading. These are positive angles, 1st quadrant. These are negative angles, 4th quadrant. It's the numerical value that I'm talking about, right? Where on your all sine tan cos. If I said to you, where is negative pi upon 4, right? The angle, negative pi upon 4, not the x coordinate, right? So you're looking at the x coordinate in the 4th quadrant, but where is the angle, negative pi upon 4? Isn't that angle in the 4th quadrant?
Oh, okay.
Right? So Never thought of that issue, but now you've brought it up. It's the first and fourth quadrant, and it's the angle that's there, right? The X value, you know, is what it is, but that's what it is. The guy that I just noticed here, and I want to put him down now because is that guy. So while you're getting ready to do this, will you put your last name down for attendance? Because we're pretty darn close to finishing. But I know that you couldn't do that with a sine and you couldn't do that with a cosine, right? Because wouldn't they be, you know, undefined, right? They don't exist, right? But what about a tangent? Is that possible? What would the tan of the inverse tan of 7 be?
7.
It is 7. So tangents and inverse tangents, if you put one of each, you're going to get the guy, right? And so be a little bit, you know, if I'd said to you the sine of the inverse sine of 7, wouldn't you say that, you know, that was undefined? But you can get an angle whose tangent is 7, right? Can't you get an angle whose tangent is 1,000,000, right? No. Tangents, you can get any answer, right? You can get an angle, you know, of 4 billion, right? So sines and cosines, be a little bit more careful than tans. And that is all we have time for. So hopefully I've covered enough for you to do your homework and get ready for your online test too, which will be due midnight on Sunday. And I believe it's visible right now.